Chapter 6, Bending Part C, Shear and Moment, Example 2. Let's consider a two simply support beam with a length of L handling a concentrated load of P at its center. So in that case, RA and RB handling a equal uh, load of a half of that load, so that's a 1 over 2 times P for RA and both for RB. If you want to draw the shear diagram, we can just go up by the amount of RA, and then there is nothing to contradict us by traveling right far to B from A, and all of a sudden there is a step, downward step with the amount of P, so it just brings us to a negative P over 2, and again there is nothing from center to B, and all of a sudden a support brings us back to 0. Mhm. So that's the shear diagram. And if you want to draw the moment diagram, it's just area under shear gives us the amount of moment. So that's a L over 2 times A. So that's PL over 4. And that's the maximum amount of shear. And likewise at the other support, there is it's a ball support, a simple support, so there is no moment, so it just you connect the two dots by a line. It just gives you the connection of center to support B. So again, if there is nothing in load, it just goes by constant line in shear, because there is the a company of support at A, and it just moves all the way to the right, halfway to the right to the center. And if shear is constant, it's 0 degree, followed by a 1 degree or a linear moment. Let's review other example with the same kind of beam, different loading. So the same beam, the same simple simple support beam handling a distributed load all over the beam. So that's again RA and RB. Each of them handle a half of load, so that's a WL over 2, and RB is the same like RA, and that's WL over 2. Half of the load goes to either sides. So if you want to draw the shear, it just goes up by the amount of RA, and just by a linear relation, it's a decreasing, uh, it's a constant load, a, a linear or 1 degree in shear. So this is a constant. It constant loading goes by 1, so that's a 0 degree. And it just goes by a 1 degree. Mhm. And if you just want to know what's happened next, it just bring you back to the other end. And if you want to draw the moment for that, so definitely this is a second degree, 1 degree higher than shear. And again, because it's to simply support, there is no moment at either sides, and the amount of maximum and maximum is equal to the area under shear. So area under shear here is a WL over 2. Mhm. And if we just calculate the area of this triangle with the length of L over 2 and the height of, so that's a half of height times length. So that's the amount of M maximum, and that's equal to WL squared over 8. That's the amount of maximum moment at the center, and that's due to symmetry as well. Let's observe the same beam with a different loading. So far we observe the behavior of a simple support beam with a concentrate at center and a distributed load all over the span. Let's consider the same configuration. It's again the same beam, but happen to handle a two-piece triangular distributed loading. Let's see how that goes. So in such case, again, RA due to symmetry is equal to RB. I strongly recommend you to just go by geometry before doing any mass. So if it was like a WL, like previous problem, it was a WL over 2 and it's a WL over 2. As you can easily see, the area goes by half. So it is, if we add these two parts, it's a triangle goes to a rectangle. So the area of our shape, which is the black two-piece triangles, it's a half of the total. So that says this is WL over 4. So forces goes by half if the total load is halved in comparison to the red rectangle, so the load is going to be halved. Mhm. Let's go by the original shape now. Then we have the forces. And if you don't agree, just go by the moment equation and summation of forces. The total load is a half of uh, WL over here and so that's the total load is W half of WL, because this part it just goes by a force of WL with the same amount of load. It should be cancelled out and the other the same, and that's the area times the distributed load. And if we want to draw the shear, so this is, if you remember, this is a linear loading, so that's a linear or first degree. So loading is just shearing, it just comes up by a WL over 4 and just goes like this by a second degree curve, and due to symmetry, second degree. This is first degree goes by second degree in shear and third degree in moment. So if you remember, how we calculate the, let's go by, do you remember we talked about a parabolic spandrel? So in that term, this is a second degree. This is a second degree as well. So this area is a 1/3 of a, this is 1/3. So the other one, it just goes the area of R, it just goes by a 2/3 of, it's 1/3 of BH. Our area is 2/3 of BH. Mhm. And why we need that area? Because the amount of moment is the area under shear, and that's the B is our length, and H is WL over WL, a quarter of WL. Let's see how that goes. And moment is a second degree. we need that area for the maximum amount of m. Mhm. And that's a M maximum is the area under 2/3 of WH. So that's L over 2 times a, a quarter of WL. So if you do the math, it gives you, so this is cancel out with this one, and maximum is WL squared over 12. The other interesting part for this problem is when you want to observe do you remember the slope of moment is the numeric value of shear. So the amount of shear, the numeric amount of shear is decreasing. So the slope is should decrease to the slope of moment should decrease from something to all the way to a horizontal line which is a zero slope. Thank you.